Ever wonder how computers find the shortest route between 2 points? Finding the shortest path is commonly referred to as pathfinding and is used in daily applications like map apps and in games for moving virtual objects and characters. I'll be giving a primer on the basics of pathfinding for a grid-based system with an interactive example. This example is a simplified version of what is used to run games like Civilization or XCOM. Pathfinding algorithms apply in many situations, which includes topics such as board games like Power Grid or On Tour. I'll be keeping today's lesson to just pathfinding, but these algorithms and data structures can be extended to more general problems. The code for the example and visuals in this project is all open source at the link in the description with a demo you can check out as well. The goal of the pathfinding algorithm is to efficiently find a path from a starting point to a destination. The quality, or goodness, of a path can be measured in a few ways. 1. The length of the path found. 2. The time it takes for the computer to find a path. And 3. The amount of stuff the computer needs to remember at once when finding a path. Each of these attributes is important for the overall performance of a given algorithm. The algorithms covered in this series will include A*, depth first search, breadth first search, and hill climbing. Many paths can take you to a destination. However, some paths are better than others due to being much more direct or shorter in length. Traveling to the other side of the city and back will get you across the street, but it would be quite inefficient. The time it takes to find a path, also called the time complexity, keeps an algorithm responsive. Waiting minutes or hours to find a route to the local store of your phone would be unreasonable for most users. Finally, the amount of stuff the computer needs to remember, called the space complexity, measures how much memory you need to compute this answer. Computers have limited resources and can only remember so many things at a given time. This demo uses a hex grid, but the code does support a square grid. However, adjacency is easier to solve for with hexagons. Also, hexagons are the bestigons. Each hex in the grid is connected to the 6 adjacent hexes it shares a side with. All the hexes are labeled with a location defined by an x and y coordinate and has adjacent hexes in the adjacent rows and columns. Every other column is offset by half to make sure they line up correctly in a hex layout. Computing the adjacent hexes coordinates is a little tricky as even and odd columns compute adjacent hexes differently. Writing down an example helped me understand how they are organized. Additionally, some of the hexes on the map can be marked as blocked and cannot be included in the path. So, now that we have the basics of the grid down, let's watch an example of pathfinding. On the left side panel are the controls for the visualization. On the right side panel is a legend which describes each kind of symbol and pattern on the map. When I right-click on a hex, I will block it and it cannot be included in the path. If I left-click on a hex, I will select the starting point for the path. If I left-click again, I will select the destination point. Once the start and destination have been selected, the pathfinding and visualization will start. From the controls panel, I can modify how fast or slow the algorithm runs, pause the current animation, and slowly step through each part of the process. On the screen now, you can see how hexes are being searched. When a location is searched, a path is created from that location back to the starting location. This will continue until the algorithm is able to find a path from the start to the destination. It will also stop if no path can be found. Right now, I have the breadth first search algorithm selected. Using a drop-down on the left panel, I can select from other algorithms. Now that we have seen a sample of the pathfinding, let's investigate how this algorithm works. From this example, I will be using the breadth first search algorithm, also called BFS for short. The BFS algorithm relies on a basic set of steps. 1. Remember what locations have already been searched. Mark the starting location as searched. 2. Queue up all locations adjacent to the starting location. 3. From that queue, remove the first location, also called a dequeue operation, and check if this location has already been searched. 4. If this location has not been searched, then mark it as searched. Then, for each location adjacent to the current location, in-queue or add to the back of the current queue. Note, when in-queuing a location, also save the path from the starting location to that location. We'll get to how that's done soon. We can also skip blocked locations at this step to avoid going through a blocked tile. 5. Repeat steps 3 and 4 until the destination is found when dequeuing a location in step 3 or the queue is empty. This algorithm will repeat until we have found a path from the starting location to the ending location, or until the queue is empty and no path can be found. The key points to remember are: 1. We do not search locations that have already been searched, and 2. Locations adjacent to the currently searched locations are labeled as queued in our visualization, can be added to our list of searched locations. Given these key points, a pathfinding algorithm will have to decide a strategy for how to search the adjacent locations to the currently searched area. When queuing adjacent locations to be searched, BFS uses a data structure called a queue, which follows a first in, first out rule, leading to this elegant branching structure that grows out evenly in all directions from the source. This will ensure that we always find the shortest path from the starting location to the ending location. To evaluate our algorithm against the properties we identified earlier, we can evaluate the quality of the path found by the algorithm by measuring the length of the found path. The length is the number of hexes we need to travel between from the start to the destination. A good algorithm will always find the shortest possible route. The number of steps the algorithm takes to find the final location is proportional to the time complexity of the algorithm. In the visualization, this can be measured by the number of hexes labeled as searched. The number of locations that are marked as searched and queued on the screen are proportional to the space complexity of the algorithm. This is because the computer needs to remember all the locations we have searched and will search next. It is important to note that these measurements may vary greatly depending on how elements are enqueued or dequeued, though. The other algorithms, depth-first search, A*, and hill climbing, work in similar ways but have different methods of enqueuing and dequeuing elements. I'll go more into detail as to how these are evaluated in future videos in the series. The way the path is saved when we search a new node is called an inverted tree data structure. This recursively saves the path to a given destination using the path at a previous location. This allows for combining paths and saving computing time and space. This data structure is visualized using the lines drawn on the searched locations, creating that tree or web-like structure branching out from the start. I will review this data structure in greater detail in a future video. Additionally, in future videos, I will be covering each of the algorithms implemented in the demo. The 4 currently implemented algorithms are 1. Hill climbing, which just takes a step towards the end and will backtrack to the previous location if it is blocked. This is a natural way of searching to take the step closest to the endpoint, but can fall into local minimization optimization problems. 2. Depth-first search, which will find the adjacent locations to search using a stack which follows a first in, last out rule. This leads to fully searching a single direction until hitting something before changing direction. Breadth-first search, which was discussed briefly earlier, adds adjacent locations to search using a queue which follows a first in, first out rule, leading to this elegant branching structure that grows out evenly in all directions from the source. And finally, A*, which uses a priority queue and heuristic to search locations most likely to be the path to the destination first. This should save on computing time on how many total locations need to be searched. However, this does incur extra cost when enqueuing and dequeuing elements compared to DFS and BFS. Diving deeper into how those 4 algorithms will be the next videos planned in this pathfinding series. I will also go a bit over graph theory and various applications of these algorithms beyond just games. Links to the GitHub project, documentation, and the interactive demo are listed in the description. Check them out if you're interested to see how they work for yourself. The demo will even work on a mobile phone via the website, although the controls might be a bit small. These videos are a bit more in-depth than the other Open Kinematic Character Controller series, and I will continue to make new videos in both series over the next few months. I've also got a lot of great feedback when sharing these visualizations online, so make sure to leave a comment if you have any questions, ideas, or suggestions. I read and respond to every comment on these videos. Thanks for listening to the end of the video. If you stayed around this long, you're probably interested in these technical algorithms like me. If you aren't already, subscribe to the channel if you're interested to keep up to date on future videos in the series. Have a great day!